Okay, this is a continuation in a series of videos whose express purpose is to help you learn how to solve various kinematic problems effectively and quickly using the Suvat method. Now, I'm assuming that you have seen the introductory video, which is part 1. A link will be in the Show More part of the section below the screen here, so you can click that to go to that video. And just to briefly show you what's in the introductory video, it is a fairly detailed video on the rationale behind the Suvat method, and also reviews general kinematic concepts and terminology and equation derivations. So you can pause the video if I'm scrolling too fast. Okay. Let's just remind ourselves that when we look for whether we're going to use the Suvat method, is first we have to identify it as a kinematic problem. We're looking for objects that are undergoing constant or uniform acceleration or deceleration, and then we're looking for at least 3 out of the 5 SUVATs, Suvats. We need at least 3 out of the 5 to solve for our answer. And we're not dealing with newtons or kilograms or joules. No forces, mass, or energy in a kinematic problem. Just to review the steps before we get into these few problems here. It's a 4-step method, and it's 1, you write the Suvat vertically. 2, enter 3 out of the 5 variables next to their letter. 3, you circle the variable that you need. And 4, you draw an arrow through the variable that's left and use the equation that's affiliated with that variable to solve for the circle variable. So you essentially should have something that looks akin to this. 3 out of the 5 Suvats are given to you in the problem. Circle the one you're looking for and then draw a line through the variable that's left with the affiliated equation. And we'll show those equations throughout our problems to help you continue to memorize them. So we basically have a Suvat method that is just a simple algorithm type methodology to get you to the equation you need quickly while you're taking the MCAT or some other time proficiency physics exam. So let's jump to the first problem here today. And we've got a driver who is moving at a constant speed of 20 meters per second, sees an accident up ahead and hits the brakes. If the car decelerates at a constant rate of -5 meters per second, how far does the car go before it comes to a stop? Alright, so the first thing we want to do is identify that this object is undergoing some type of constant acceleration or deceleration. And in our problem here, we see that there's a deceleration at a constant rate. So we've got a kinematic problem. They're asking for how far the car is displaced before it comes to a stop. So step 1, we're going to list our letters Suvat vertically, and then fill in 3 out of the step 2, fill in 3 out of the 5 variables. So what do we have? We've got a car moving at a constant speed. So it's at the time that we've come across this problem, our initial velocity would be 20 meters per second. It's positive, so we'll just assume that positive is going to go to the right. And we have a negative acceleration of -5 meters per second squared. So that makes sense. We've got an object that's going to the right with 20 meters per second, and we've got an acceleration that's going in the opposite direction of -5 meters per second squared. So when acceleration and the velocity are in opposite directions, then that object necessarily slows down. Okay, so that's what we are having happen here. And then we need one more bit of information. And if the car decelerates, how far does it go? Okay, so the last bit of information is going to be our stop. our final velocity will be 0 meters per second. Now, step 3, we're going to circle what we need. We need how far it goes before it comes to a stop, so displacement is what we're looking for. And then step 4, we draw a line through the variable that's left, and we use the affiliated equation, which is v squared is final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the displacement. All right, so we see that we have this problem here, this equation here, and we're looking for that. So let's look at the math here, and we're just going to fill in the bits of data that we have, and we're solving for S. And so when you move everything around, we've got 0 meters per second squared minus 20 meters per second squared, and then we're going to divide by -5 times 2, -10. We divide both sides by minus 10 meters per second. We'll bring that over. I skipped a step there, I apologize, but I'm assuming that you algebraically know how to do that. So we ultimately end up with this on the left and solve for S. And notice that up top we've got meters squared per second squared, meters squared per second squared when we do the math there. And on the bottom we've got meters per second squared. So the units that will cancel out is we've got meters squared. We keep one of the meters up there, that cancels out, and the s squared cancels out. In previous videos I've gone over the analysis of how these units cancel out, so I'm not going to show you there. I assume that you've seen those other videos. So our answer is 40 meters of displacement. And that is one of the answers. Okay, fairly straightforward problem. Just keep aware of the fact that it's very important to put the right signs in, because we've got vectors. Everything's a vector in Suvat except for time. So you always have to be aware of the signs. All right, next question. We have an object. If an object is dropped from a height of 80 meters above the Earth, how long does it take to reach the Earth? So first thing we want to do is ask if there's a constant acceleration imparted on this object. And yes, this is a free fall problem. It's one-dimensional, and we'll assume that there's no air resistance to contend with here. And so we've got just a minus 10 meters per second squared. I rounded off from 9.8. And so we've got a Suvat problem, and we do step 1. We list the Suvat letters vertically. And then step 2, we fill in 3 out of the 5. So what do we have here? It's kind of implicit here on some of the data. It's implied that this ball was dropped, so it's implied that the initial velocity is 0 meters per second. We don't have a hand here, but we'll just assume that somebody's holding it, or whatever, for whatever reason it's dropped at 0 meters per second. And so we'll put that in there. And then we have acceleration is minus 10 meters per second squared. And then we want to know if the object starts from height above the Earth of 80 meters. So we've got displacement. Now here's the thing that's important is remember the displacement is going down, and I'm going to use this as our starting point where we drop the ball as 0. So anything above the dropping point is going to be positive, and anything below that dropping point is going to be negative. So we're going to put negative. So the ball is going in the same direction as the acceleration vector. So important to watch those signs, otherwise your math won't work out. Okay, so that's step 2. Step 3 is to circle the variable that we need. How long does it take? So we circle time, and then step 4, we draw a line through the variable that's left. And so we're going to use the equation that's affiliated with that, which is displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. Alright, so we go down and look at the math for this. And I leave my problems in their pristine form and then rearrange them after I do the math, because sometimes like this you'll see that it makes it easier. So we've got 80 meters, S is equal to U, and T is what we're looking for, and we've got A, we've got that, we've got that, and we've got that, and we're looking for time. So we're lucky in this situation, since we're starting with the initial velocity of 0, that we don't have to solve for a quadratic equation, our t's, t squared and t here, because this drops out. And so we end up with minus 80 meters is equal to minus 5 meters per second squared times time squared. Divide both sides by minus 5 meters per second squared. We do it on the other side, and we end up with this below here. And now before we do the square root of each side to get rid of this square sign, let's clean up our units a little bit. And in this situation, this will cancel out that, and so we end up with second squared on top. And now we take the square root of both sides, and second squared is going to be seconds. Square root of 16 is 4. Square root of t squared is t. So we've got 4 seconds is equal to the time, and that is our answer. Alright, let's take a look at the next one. Alright, this is a good problem because a lot of times a Suvat problem, we've done a couple today that are fairly straightforward, and this one is too, but there is a little bit of interpretation that you have to do, and so it's not as straightforward as some of the other ones that you've seen so far in these series of problems. Alright, if an apple is dropped from an altitude of 100 meters, if an apple is dropped from an altitude of 100 meters, reaches an altitude of 80 meters in 2 seconds after falling for 2 seconds, what altitude will it be in 4 seconds? Okay, so the easiest way I think to do this problem, well, first let's make sure it's a Suvat. Well, it's a free fall problem again. We're under the influence of G, which is rounded off minus 10 meters per second squared, and that's downward. So we've got a constant acceleration imparted on our object, and so we're going to do Suvat. Step 1, we list our Suvats vertically, and then we put the information in. So what we have is we've got an object that's got an initial velocity of 0 meters per second, because it's just dropped at that point, it's still, and it's got a minus 10 meters per second squared acceleration, and we know that in 2 seconds it's fallen 20 meters. Okay, so we want to know how far it will have fallen if it continued to fall for 4 seconds. So the easiest way to do this is just figure out how far the displacement will be at this point, and then, in other words, from 0 time to 4 seconds. So don't let this information that's over here really, at that point you don't really need to confuse the issue. Make it as easy as possible on yourself. So we're going to put 4 seconds down here and pretend like this is a problem where we're interested in the displacement. Step 3, we circle the thing we're looking for. We're interested in the displacement of what this displacement would be after 4 seconds. And then step 4, we're going to draw a line through the variable that's left, use the equation that's affiliated with it. It's the same one we used in the previous problem, and solve for S. Okay, so we'll do that. And so what we have here is we're solving for S. Initial velocity is 0 meters per second. It fell for 4 seconds. We plug in our acceleration and our time. So we end up with minus 5 meters per second squared times 16 seconds squared. The seconds squared cancel out. So we're left with minus 5 times 16, or minus 80 meters. Okay, so that what we just did there was keep things simple, and we found that this displacement was minus 80 meters. All right, so that means that if it was an altitude of 100 meters and it fell 80, the current altitude here is 20 meters above the Earth. So that's what they're asking for, though. So we had to use the Suvat problem, but we have our question worded so that we have to take it a little bit further. So we have 100 meters, and we found our displacement was minus 80 meters. So we've got that, and we're left with 20 meters left. So our ball at this point, our ball would be at an altitude of 20 meters. And so there's the answer. Now I do want to show you another way to look at this, because I think it's good to see different opportunities to use Suvat. So let's take the same problem. We're going to look for the same thing. We're interested in the altitude, but I just want you to realize that if the ball fell for 2 seconds from here to here, at that 2-second interval, the velocity of the ball would be minus 20 meters per second. Now you don't need to know you don't need to use Suvat to know that, because the definition of acceleration is, and let's take a look at this way it's usually written, minus 10 meters per second squared. But what that actually means is that we're going minus 10 meters, we're losing minus 10 meters per second every second. So in other words, this velocity is changing. It's going, because it's going down, you could say, and it's negative, that the velocity is increasing by minus 10 meters per second every second. So that's a real easy calculation. We know that after 1 second, the velocity would be minus 10 meters per second, and after 2 seconds, at this point, it would be minus 20 meters per second. So velocity is directly proportional to time, and we'll get into the shortcuts in a later video. But let's just say that we knew that, and now we can turn this into a Suvat equation or Suvat problem strategy that is going to give us the same answer, but it's got a different approach. Let's pretend like we're interested in at this point in time. So this is where our interest starts in the ball, is at this point. So we're going to say that our initial velocity is minus 20 meters per second. We have the accelerations the same, but we're talking about this interval between here and here, and that's it falls for 4 seconds total. So we've got another 2 seconds here. So we put that in there instead, and we're just interested in what is the displacement between this the second 2-second interval. Here's the first 2-second interval here where it fell, and now we're interested in the second 2-second interval. But at the second 2-second interval, at the very beginning of that interval, the initial velocity is minus 20 meters per second. So we're going to go ahead and we're still looking for the displacement in this scenario that we're creating here, and so we're still going to draw our line through the remaining variable v. We're just plugging in different information. It's minus 20 meters per second for u. We got 2 seconds now. Our acceleration is the same in 2 seconds, and you're going to find it. You got minus 40 meters and then minus another 20 meters. So this is, our displacement is minus 60 meters. So that means that between this point, it's minus 60 meters. And then up here, it fell, they told us this in the problem, it fell minus 20 meters. So again, we're minus 80 meters total in the 4 seconds, which is what we found in the first approach. And we subtracted from the initial height, initial altitude of 100 meters, and we still end up with the same answer. Now, I would never do the problem this way. I would do it the first way because it's a much easier strategy. But I just wanted to take the opportunity to show you this way because it lets you realize that at this point, you know, we have a different velocity. We've got a time interval that's 2 seconds instead of the 4 that we used in the first, and so forth. So anyway, you can take that for what it is. The first strategy is the best. All right, so we're going to continue doing more problems in the next video. They're going to start getting a little more difficult. Occasionally I'll put some easier ones in just to keep the morale up and keep the practice going with what we've previously learned. But we'll start looking at some different types of kinematic problems with a little more twist to them, like this one with the altitude. All right, see you next time. Bye-bye.